Welcome. I'm going to introduce work, energy, and power, and you can follow along with your own version of this. You also have this sheet that you can use. All right, so there's a link to this sheet if you'd like to write things down, or you can wait till the presentation's over and and download a copy of the final sheet if you like. All right, so we're introducing work and energy. All right, and everything, all the slideshow is meant to kind of come back to this sheet if you want to record things there, right? So every slide that you're going to see is some kind of blown up version of these guys. All right, okay, so let's start with the definition. Work is the transfer of energy to an object when a force is applied over a distance. Okay, now this is similar to the idea of impulse, right? Because when you apply a force for a certain amount of time, which is an impulse, you're usually also applying a force and moving something through a distance. So when you apply an impulse to an object and change its momentum, you probably are also doing work on the object. And they're just different ways of looking at the same thing, right? Work and energy is a different way to look at some of the same things we've been looking at all year, and in some ways, a different way to solve the same problems that we've been doing all year, right? Okay, so simple formula is work is equal to force times distance. But for work to be done, a force must be applied and the object must move in the direction of the force. All right. For example, Peta here is lifting an object, so he's working against gravity. Okay. Or Katniss is pulling back on a bowstring, right? So she's working against that force on that string, right? Now the unit for work, if you just carry your units through, you'll see that work is measured in Newton meters, but we have a special name for that called a joule, not to be confused with the J for impulse. Just like little m is both mass in meters, big J is both the unit joule and the quantity impulse. Okay, you can either use a Newton meter or a joule, and then of course, since a Newton is also a kilogram meter per second squared, a joule is also a kilogram meter cubed per second squared. If you really want to, any of those equivalent units would be fine, but I usually just use joules because it's a letter, one letter. Okay. All right. Work can also be done to transfer energy to an object when be used to change the velocity of an object. So what Fred's doing here is he is applying a force with his feet against the ground over a certain distance, and he is giving energy, changing the velocity of his car. Okay. All right. Now, here's where work is a little bit different. It is scalar, okay? That doesn't mean you can't have negative work, but negative work means that you owe some work. It doesn't mean like work to the west or work to the south, okay? There's no such thing as a direction of work. It's scalar, okay? And the other thing about this formula that's different from the impulse formula is that it's a specific force. It is not the net force, all right? That's not something we emphasize, but when you did the impulse formula, that was a net force times a time that was equal to impulse. Work is a single force. So think about this object on an inclined plane, right? There are all these different forces on them, all right? But if the object is moving parallel to the plane, the only force that matters is the ones that are parallel to the plane. Okay. All right. So for that reason, we also have all different kinds of work that we can describe with these different forces, right? There's the work done against gravity, if we're talking about the force of gravity. All right. There's a work done by the applied force. There is work done due to friction. Nightshade's coming over to say hello. And in this case, the normal force does no work because the object is not moving in the direction of the normal force at all. Okay, so that specific force can make work problems a little bit more tricky. Okay, energy is like the flip side of work, right? So if we go back, work is how you transfer energy to an object, and energy is the ability to do work. Okay, energy is also scalar for the same reason, and it is also measured in joules. Okay, and we're going to look at there's all kinds of energy. All right, but specifically in this class, we're going to concentrate on mostly on the mechanical energies, which are your potential energies. Actually, there's two types of those we're going to learn, and kinetic. Okay. All right. And then one last thing is we should talk about internal energy, which is given by the letter Q. And this is another place where your reference tables use the same letter for two different things. Q is both charge and internal energy. So just watch out for that. Okay. So internal energy is all the energy of the atoms that make up an object. Okay. And that can be things like heat. It could be energy due to the mass of the object. All right. But the only way that internal energy changes in physics class, in a way that we're going to look at it, is work due to friction. Okay? All right. And we'll come back to that in a little bit. Okay. Let's take a brief moment to talk about simple machines. All right. So why do we use simple machines like an inclined plane? What is the purpose, right? Why do we slide a box up a ramp? Why don't we just lift it? Why do we take stairs? Why don't we just jump to the second floor? And so if we do use an inclined plane or another kind of simple machine, does it save us work? Okay. Well, let's look at this. Okay. Again, we said before that work is, you have to talk about which specific force we're talking about here. So when we move this object up an inclined plane, you can think of the work being done against gravity, which is the force of gravity times height. Okay. And again, when you're doing work problems, the force and the distance it moves through should be parallel. More on that in a bit. Okay. And we might call that work out because the reason that we're trying to like move this box up a ramp is to frickin' get the box lifted, right? Then you can say the work in is the work done by the force applied. All right. And then the distance in this case would be the length of the ramp. Okay. Now, in a perfect world, these might be equal, right? If there was absolutely no friction, then I would expect the work in to be exactly equal to the work out. But because there probably is friction, it will probably take a little bit more work to move something up a ramp than it does to simply lift it because there's more friction. So the work out is going to either be equal if there's no friction, or it's going to be a little bit less than the work you're putting in. One thing that's not true is there's no way to make a simple machine do like reduce the work. There's always a trade-off, right? So if you're reducing the force, and notice that the force applied is lower than the force against gravity, right? Then the trade-off is that the length of the ramp is longer, right? Or if you use this larger force, then the trade-off is that the distance of the height that you're lifting it is shorter. There's always a trade-off. Simple machines cannot save us work. In fact, they're probably increasing it due to friction. But unless you're a cat who can take a standing 12-foot leap, you're going to need to use the ramp or the stairs to get upstairs because you simply don't have the force, the ability to do it with just your muscles. Okay. And then let's talk about work due to friction. Okay, so we said that work is equal to force times distance. So one of the ways you can figure out work due to friction is to actually look at the frictional force and multiply it by the distance that's parallel to that. All right, if we go back a couple slides, you can see there's this force of friction, and then the distance would be the distance it moves along the ramp that's parallel to that. Okay. All right. Excuse me. It's not COVID. All right. This is not the most common way to do work. All right. Another way to do work, all right, is to think about the difference between the work in and the work out. If they are different, it's because of friction. All right. So if the work done in, say, lifting something is less than the work done in moving at that same height up a ramp, then the difference, the reason these aren't equal is because of friction. So the other way to figure out work due to friction is to find the change in work or the change in energy, okay? Because work is also equal to change in energy. This formula is on your reference tables, by the way. And then the last thing is to talk about this internal energy, right? So the only way internal energy is actually changing in physics class is with friction. You're not changing, we're not heating things up with Bunsen burners. We're not changing the mass of things or converting some of the mass to energy in any kind of sizable amount, right? If things are changing their internal energy, it's because they're heating up, and they're heating up because of friction, right? Okay, so in this class, friction is also going to be equal to the change in internal energy, all right? So there's all these different ways to figure out work due to friction. Okay, now, There's also some weird examples, okay? There are times when there is no work. For example, they'll often have a problem where someone's like doing something really heavy, like trying to hold a piano on a ramp, right? And clearly this has got to take some work, keeping this rolling piano from rolling down. I mean, this person must be doing work. But here's the key. If the piano isn't moving, then there's no work done on the piano. His muscles may be moving, all right, like squeezing and stuff. So his muscles may be doing work within his body, but there is no work done on the piano if the piano doesn't move. And similarly, if the object moves perpendicular to the force, like orbit, okay, so if you think about the moon orbiting the Earth, all right, in its nearly circular orbit, the pull of the Earth's gravity is towards the Earth, and the velocity at any moment is perpendicular to that. The moon is not, the pull of the Earth is not doing any work on the moon. And that is a very good thing. Because if the pull of the Earth was doing work on the moon, we'd have to keep putting energy in, all right? And then the orbit wouldn't be stable, all right? And we wouldn't keep the moon, all right? And the same would be true for us orbiting around the sun, right? If we had to put energy in to keep us orbiting around the sun, then we wouldn't keep orbiting the sun and we wouldn't be here to wonder about it. Okay? All right? So let's just talk about a few of those examples. All right? So if the object doesn't move, I guess we lost the word move here, or the object moves perpendicular to the force, the work is equal to 0. Okay? On the other hand, all right, if it's on an inclined plane, you've got to make sure that the force and the distance are parallel to each other. So that could mean that you've got to do some trig, right? So if they gave you the length of the inclined plane but didn't give you the height, and they gave you the angle, you could use trig to find the height. All right, and then you need to make sure that that force goes with that height. Or let's imagine you're pulling something like a wagon, right? Or a sled. You're probably pulling at an angle, okay? But all of that force applied is not doing work. Only the part of the force applied that's actually in the direction of movement, all right, is actually doing the work. So in this case, only the x component, which I've shown in red here, is doing the work. And if you go back to your good old reference tables, the x component of a force is given by the force times the cosine of the angle. Okay, this formula here, work equals force F cosine theta. Oh, and I forgot the D. There's supposed to be a D down here, and for some reason that's not there. So this should say work force applied cosine theta times the distance, and for some reason that didn't get transferred, and I'll have to fix that. All right. Yeah, so one of the formulas for work, like that you'll see, is F cosine theta times D. And that's because of this idea that only the one component is actually doing the work in this case. All right, finally, sometimes we don't just care about the amount of work being done, but we want to know how fast it's being done, and that's power. Capital P for power, all right? Not to be confused with little p, which is momentum. All right, so power is the rate at which work is done or energy is transferred. And again, like back in some other formulas, this is how it's written on your reference tables, and it's not very user-friendly, right? Like you're going to use one of these three formulas, okay? You should also, so power is either work over time, it's also energy over time, turns out, or since work is force times distance, assuming that the force and distance are parallel, power is also force times distance times time. And then since distance over time is actually equal to velocity, another formula for power is force times average velocity. Okay. Finally, the unit for power is a watt, given by capital W, not to be confused with capital W for work. And a watt is a joule per second. Okay. And here's what we got. Again, I've got to fix this to say D on it, and I'm going to fix that in a second. But all right, there is your introduction to work. Enjoy.